Welcome to The Explainer. I am so thrilled you're tuning in today because we are going on a seriously fascinating mathematical journey. We're going to demystify continuous time systems and learn exactly how to find this beautiful, predictable structure hiding right in the middle of pure chaos. And honestly, the best part? We're going to do it using a remarkably elegant, simple tool, local maxima.
Okay, let's dive right into this. Here's our roadmap. We'll hit continuous time and chaos, visualizing the butterfly effect, finding order with maxima, plotting the bifurcation diagram, and finally, code your own chaos.
All right, section 1, continuous time and chaos. Let's just quickly establish the kind of mathematical playground we're working in today. When we talk about continuous time systems, we mean systems that evolve seamlessly over a continuous interval, usually starting from a time of 0 and just stretching infinitely onward. Because they're continuous, they're described by differential equations. But here's the trick. When we actually want to solve these highly nonlinear, chaotic systems on a computer, we use numerical techniques. Basically, we slice that continuous time into tiny, discrete intervals, like 0.001 seconds, and solve it step by step.
Just to anchor this in reality for a second, let's contrast it with discrete time systems. Discrete systems jump from one fixed interval to the next, right? Think of annual economic cycles or a yearly biological population count. But our focus today is entirely on the continuous side of the universe. This is literally the math of physical reality. We're talking fluid flows, physical circuits, mechanical systems smoothly transitioning from one exact moment to the next.
But for this all to work, there is a golden rule. Number 3, for an autonomous continuous time system to actually exhibit chaos, it absolutely must have at least 3 dimensions, or 3 states. A 2-dimensional system simply cannot be chaotic. Why? Well, in a continuous system, trajectories can never intersect themselves. So you need that 3rd dimension to give the chaotic flow the space it needs to tangle and weave without ever crossing its own path. Moving right along to section 2, visualizing the butterfly effect. Let's look at a real-world mathematical model, the classic Rossler system. It perfectly follows our golden rule with 3 states, x1, x2, and x3, and 3 tunable parameters, a, b, and c. Now, what's really wild here is how we choose to look at the data. Normally, you'd plot a state, like x1, over time. For a chaotic system, that just looks like a messy, non-repeating wave. But if we plot the 3 states against each other, x1 versus x2 versus x3, we get a phase portrait. The solution never repeats, meaning it's aperiodic. But it doesn't just spiral off to infinity either. It's totally bounded. It forms this mesmerizing, beautiful shape known as a strange attractor.
And chaotic systems, like our Rossler attractor, have a very famous property. Imagine starting 2 simulations with almost identical starting conditions, a difference so unbelievably small it's just 10 to the power of -4. For the first 100 seconds, you literally can't even tell them apart. The trajectories overlap perfectly, but slowly that minuscule difference compounds. By 105 seconds, they've completely diverged into totally different solutions. This right here is the actual mathematical proof of pop culture's favorite concept, the butterfly effect.
Before we can truly analyze all this, we gotta do a little housekeeping. When you first start simulating a system, it hasn't quite settled into its true rhythm yet. It kind of oscillates and wanders around as it transitions from your chosen starting point into its final behavior. We call this initial warm-up period the transient. So here's your practical takeaway. When you're mapping chaos, always discard the transient. Just toss out the first 50 to 500 seconds of your simulation data. We only care about that settled behavior. Section 3, finding order with maxima. Now that we've cleared away the messy warm-up data, we arrive at the absolute best tool for decoding this chaotic noise, counting local maxima. So, the crucial point is this. We can quantify exactly how a system is behaving simply by picking one state, looking at its peaks, and counting the distinct local maxima. If parameter A is 0.3, the system repeats a single curve, one local maxima. We call that period 1. Change A to 0.35, and suddenly the curve does a double loop, 2 distinct local maxima, or period 2. Bump it to 0.38, you get 4 maxima, period 4. But if you push parameter A to 0.45, the whole pattern completely shatters. The maxima become innumerable, completely dispersed all over the place. That, my friends, is pure chaos. What you should really take away from this is that the descent into chaos isn't just some random event. It happens in very specific, mathematical steps. As we tweak that parameter A in the Rossler system, the single repeating path splits in 2. Then those 2 paths split into 4. Then 8. then 16. It keeps doubling faster and faster until the pattern completely shatters into those uncountable, chaotic maxima we just talked about. Section 4. Plotting the bifurcation diagram. Instead of checking these parameters one by one, what if we could just look at the entire map of a system's behavior all at once? Think of the bifurcation diagram like a giant puzzle made of hundreds of those local maxima tests we just did, all lined up side by side. On the x-axis, we plot the range of our parameter, say A going from point 3 to point 45. On the y-axis, we plot the local maxima we found for a chosen state at each of those parameter values. This means any vertical slice of this diagram instantly reveals the system's exact qualitative behavior for that specific parameter. And this brilliantly illustrates the real power of this visual tool. When you look at the diagram, the areas of order are super obvious. You see these crisp, solid lines representing distinct local maxima, clear repeating patterns like period 1, 2, or 4. But as you scan across the graph, those lines suddenly explode into dense, black, ink-like regions. Those dense regions are where the countless scattered maxima live. When you see a black wall on a bifurcation diagram, you are looking directly at the face of pure aperiodic chaos. But honestly, here is the most incredible, awe-inspiring detail about these systems. Chaos is surprisingly fragile. If you take this diagram and zoom all the way into one of those dense, ink-black chaotic regions, you don't just find more noise. No way. You actually discover tiny, white, vertical gaps. Inside those gaps, the system suddenly snaps back into pure periodicity, like a perfect period 3 behavior, branching into 6, then 12, before dissolving right back into chaos. Perfect, predictable order is always hiding deep inside the noise, just waiting to be found. All right, Section 5. Code your own chaos. Let's bring it all home, because you definitely don't need a supercomputer to do this. You can absolutely program it yourself. Generating this massive map of chaos is honestly just a simple loop of 5 computational steps. First, simulate your continuous system for a good long duration, say 4,000 seconds or more. Second, discard that transient warm-up behavior we talked about earlier. Third, analyze the remaining data and find the local maxima for just one chosen state. Fourth, plot those maxima vertically against your current parameter. And finally, step 5. Increase your parameter by a tiny, tiny fraction and loop right back to step 1. Do this hundreds of times and the map of chaos literally draws itself. Oh, and a quick pro tip from our source material if you want to optimize your code. There's a slight variation of this called the continuation diagram. Instead of starting every single simulation step from the exact same initial conditions, you use the final state of your previous simulation as the new starting point for the next one. Because the system is already warmed up, it speeds up convergence and reduces the transient time without altering your overall code execution time. It's just a brilliant little shortcut for continuous time mapping. We've seen today how just a handful of equations, a little bit of computational patience, and the simple act of counting local peaks can completely demystify a strange attractor. But it leaves us with a pretty wild thought to take away. If a simple mathematical trick can so perfectly map the boundaries of chaos in a mechanical flow or a physical circuit, what other chaotic, seemingly unpredictable systems in our own world, systems we interact with every single day, are just waiting for the right tool to reveal their hidden order? Thank you so much for exploring the math with us today, and keep seeking the structure in the noise.